in the power systems, one the PQ bars, and another one the PV bars. Okay, so PQ and PV will indicate that the parameters we have known, right? The PQ bars we know the P and Q, and the PV bars we know the actually we know the real power P and the magnitude voltage. Okay, so for in the power systems there will be totally 4 parameters we need to know, and the real power and imaginary power and voltage magnitude and angle. Okay, so that in each power flow questions or problems we know 2 of them and we need to solve another 2. And the third task we have to bars in previous because the snack bars. Okay, so the reference bars, so that this will be the PV bars space in and solved by the Gauss-Seidel iterations. Here's an example. So iteration for 3 steps. It's generator, reactive power limits, and we also know there will be one method to accelerate the convergence. Okay, so the acceleration parameter, the alpha. Okay, so we can get this coefficient in this formula. That's called the formula, and by doing and by setting the different values of the accelerator coefficient alpha, we can get different steps. We can get different numbers of steps or different speed to achieve the convergences. Okay. Okay, so no problems, no questions about the previous page. Okay. Do you have any problems about this? The Gauss-Seidel with the previous method? Okay, so do you have any problems or questions? What?
Is it binary?
No, it's in the previous page. The Gauss-Seidel iteration is the one iteration method, and if you have known this, and we will start another one, and you can Reactive method.
But we can do some exercise.
Exercise.
Is it better for
Exercise because we have some examples, right? So examples. The PV bars. Okay, so we'll see one examples for the PQ bars. Okay, so the PQ bars examples. So just like these 2 bar systems, we can know that here is the generator bars, and that arrow is the node buses. Okay, the shunt capacitor, the line impedance, the shunt capacitor of every parameters of impedance we have known. Okay, so the first step, the notch will have to convert the impedance to the admittance. Okay, so the inverse of the impedance lead, this. So here is the line admittance. This is the line admittance, right? Line admittance. So that the admittance bars. So you remember that for the surf admittance, how to calculate? You remember the surf admittance, that's like the diagonal elements in this matrix. How to calculate? How to calculate this surf admittance? Yeah, we have known this, but how to calculate this? So the surf admittance, and you forgot You have forgot that.
Yes,
The surf admittance for each bars is the sum of all the admittance that are connected to this one. Okay?
yes.
Okay, so you can say this is connected to the 9 admittance, right? Okay, the 9 admittance is this one, 5 minus 15, okay, right? And it's also connected with this shunt, right? Shunt is 0.05, so that the surf admittance of these bars is the sum of these two, so this is this, right? So there will be back T15 plus 0.05, okay? So that this one, and for this one, for the node bars, you are connected with the 9 admittance, the 9 shunt capacitor admittance, and here is the 9 shunt admittance, okay? So these three,
Understood.
okay, and for the mutual admittance, right? The mutual admittance,
The same.
what? No, you want to be same, right?
Mutual admittance of
What is the mutual admittance of between this generator bus and node bus? What is this?
this is minus 5 plus 15.
Yes, 5, yes.
That's 16.
Right, you're correct. So for the mutual, just to remember that it's very quite easy. The line admittance, this transmission line that were connected with two buses, okay? So, and just get the negative value of this one, okay? Minus, just like the negative of the line admittance, negative 5 minus 5 plus 15, right? Okay, so in that case, we get this admittance bars. This admittance bars, which can be reflect the whole system structure, the topology of the system. Okay. So that's next. What we need to do is that we need an initial value. Okay. So we assume that. Okay, so this 1 volt is the loading value, okay? So this is the voltage of the generator. So it's one entry HV, so it's expression of the voltage magnitude by this complex power and this, right? So this is the target equation. Okay, so this is the equation that we need to use the iteration method. Okay. So that update the V, this is the step 1, and this is the next step 2. This is the update equation. Okay, update. So we have to put every knowing parameters inside this, okay, that we assume that initial value, we assume that is also the 1 volt with 0 angle, with 0 degree angle, okay, this is the flat start, okay, so this is the first step, the initial value, and then we put H into this equations, we get this, and then by doing so, this is the 0, okay, V0, put in to get the V1, right? Then we put the V1s as the input to get another V2. We have to repeat all the steps with V2 as the input, we get the V3. And we get the V3 as input, and we get the V4. Okay. So here is a critical and none as a mistake. or the distance from the real number is close or smaller enough to and which is smaller than the critical criteria. Okay, so we'll solve the iteration, and this is our final solution. Okay, so any problems for this?
So is this equation v2 over v plus 1?
This one?
Yeah.
No, this just means that this is the update equations. Just like you put the first step, the first initial value here, and we will get the update of this value. Okay? Just like you are you're closer to the real value in each step. Because here is our initial guess, right? We get into these equations, we get a new value or updated value of this V2, right? And this V2 is closer to the real value, the real magnitude, real voltage magnitude compared with the initial guess. Okay, so that's why this is what the iteration method is doing.
So how to get this value? Number 1, number 2, number 3. Yeah.
Okay, so that number 1. Okay, so this is the first step. This is our guess, right? We assume that it's 1, and of course you can assume that this is the 2. But if you do so, maybe you will need maybe 7 or 8 steps to get close to this one. Okay, so this is the first step. And we will put the first step. We can see the first step is orange, the V, right? We put this into this, and you can say all the equations, all the parameters equations will have a specific value. You can calculate this to the V1, right? And then this is the V1. Put this into this equation, calculate. This is the V1. Okay, so at this moment, you get a more specific answer for V2 compared with the first step. And then you still need to put this V1 as the input here. Okay, so this one is this indicates the step 1. And this is a 1 plus 1 and 2, this is step 2, right? Put this into this equation, we can also get a value. This is the step 2, right? Just repeat these steps. And when you find your answer is closer enough to the real value, you say that, okay, so I can tolerate the mistake or the differences. Okay, so stop the iteration. Answer. So it's why it's the only iteration, because you know that this is the unmedium equations. You cannot get a correct answer or specific answer at first. Okay.
Yes, sir.
Okay. Correct.
When I give this V equal 1, my answer is 0.9670 and minus 0.05682.
Yeah. This is approximate value. Okay. So this cannot be a precise value, so that you can use your calculators. Okay, just to repeat for 5 times. Okay, you can get the answer. Okay.
So I have one question, sir. This V2 guess. This is our guess value, yeah?
Yeah. But Yeah, you can get, because just like you can guess, okay, so the initial value is 2 volt, and you here using the input to get answer, but in that case, I guess we will be using more
I
steps.
can guess anyone.
Yeah. But if so that the iteration, the
It's easy
speed,
if I choose 2, 1.
yeah, but it's where your initial guess will affect your converging speed. Okay, so okay, so there's an example.
With respect to
That's what it says. On angle like this, we put it up. AK power X would be losing 35.
okay, so that if we have known that V2 magnitude of V2, we can get this another or other parameters. Okay, so that everything in this system can be estimated. This measure bus. Okay, so we choose one as a reference, so that just like here is the reference bars. 0.0 degree is the reference angle, 1 is the reference magnitude. Okay, so just like a per unit, it's a just like the per unit, the base of the per unit equation. Okay, snack bars. And for many buses, okay, it's doing like this, but maybe a little bit more difficult. You can update each of the parameters by one time. You can say this initial this V plus 1, and then by the first step we can just to update one parameters. Okay, let's say the V2 is the V plus 1. Third step, we get a V3 into the V plus 1. Okay, so by each step, we will update only one of the unknown parameters on here, so that we will need n steps to update all of these parameters in this equation. So that will be very difficult, okay, because we will need n steps to complete only one update. Okay, so the 3 types of the buses, okay, because of the previous example in PQ, so that here is another inclusion of the PV bars in by Gauss-Seidel iteration methods, okay. So for the PV bars, it's only difference in that the iteration equation is different, okay? Because the Q is unknown, and we get this complex power. P is knowing, Q is unknown, so that we will save the imaginary power as a package in this iteration method, okay? So that we also will establish another equations called the magnitudes of the voltage. Okay. Okay, so in these years we'll see another example, PV bus, right? Like a very similar to bus systems. Okay, to see that there will be only Q and the unknown parameters. Okay, so there will be only another iteration equations like so, right? And here's the V, the intermediate variables. Okay.
This is the per unit value, yes sir? This V2 is per unit.
Yes, per unit, yeah. So here is also another iteration. Okay, here is the iteration, because for the PV bus we only know the magnitude of the voltage. We do not know the angle, right? So here is why we need intermediate variables. Okay, so it's right by doing this. And here we are in the same gas. There 1.05 initial gas. In that case, we see that these magnitudes, knowing about the angle, we'll assume that is 0, okay? So put inside, okay, here is the SQ. By each step, I will say that we're only focusing on this imaginary part of this complex power, okay? Reactive power or reactive power, and the X power is 0. And to say the magnitude of this V2 is approaching to the knowing value, because we know that the magnitude of the V2 is 0 and 1.05, okay? So the magnitude is also approaching to the fixed value, and the angle, you see that we are also approaching to the real angle, which is, so that PV bars just use the differential iteration equations, okay? So that makes sense that you are also to put the first initial gas into this equation and inputs to get the first update, then the first update value to get the bigger input, to get the second update, and the third and the fourth, and here you stop iteration. Okay? So that the generator, reactive power limits, so that here is the accelerated. Okay, so here is the acceleration parameters, and just like with equations, we can get to enhance or increase the multiplications of these parameters. Okay, so that we can do it according to different needs to see how fast this converting speed will need. So the Gauss method, iteration method. Okay, so if you have no more questions, we will have to learn this using Racine. So it will be actually more frequently used to calculate the power flow. Okay. So that the key idea here is to use the sequential linearizations, okay? The general form of the problem, okay? So if we need to solve this problem, we have to focus on this. When we know the x as input, and what is the function value of this when this equal to 0, okay? And so speeder. Okay, so the first step of the Newton-Raphson method, okay, so we need to choose F. So the Taylor series, have you learned about this?
Yeah,
series in mathematics?
Calculus,
Simply speaking, by using the Taylor series, we can get to divide one functions, or maybe very complex functions, to many different parts, okay, or many different sub-functions. Okay, and with the first order, the second order, third order, and then, okay, so this Taylor series. So about the power gas, the SV, okay, so the delta S will also assume the delta X deviation from the SV. So the delta, you know, is used for the criteria, right? It's to decide you to when to stop the duration, okay? That you could say that Fxv, right, this is the initial value, and here is the deviation from SV, right? That's the difference from the initial gas value to the actual value. Okay, so there is the differences. So that by the Taylor series, to say that the fxv, the original function, the first order is that differential of the x of this x in this function, and what to do with delta x, and then the second order, so the special double differentiation of these functions by twice, okay, so double differentiation by function, and then this is the square of this delta x, and the higher order terms will be the third term, the third order, the fourth order, the fifth order, and so on, okay. So this is the Taylor series. So I think okay with the page.
Weight loss.
Okay, so the second steps will approximate. So the fx, the function by mapping all the terms satisfied first or two. You see, we know that by Taylor series, maybe the third term, the third order, the fourth order, the fifth order, so the request smaller compared with the first and second order parameter. The first order atom and the second order atom, okay? So that because we are doing the iteration, so we only need to get the approximation of these functions, so that we get the approximation of these only first two parameters, okay? We only need to calculate the first order atoms in these functions, okay? Say second, third, fourth, we just to omit this, ignore this part, okay? And the third step is to say the linear approximation occur equal to 0, okay? So that we will assume that these functions equal to 0, these functions equal to 0, right? Equal to 0, and because the critical criteria for stopping that is delta x is the difference from the soft value to the true value. Okay, so this is the delta x. So the critical criteria for stopping. Okay, equal to this. Right, because this part is 0. This one is equal, and then we put this down to the denominator, right? So this is our minus. Yeah, minus and next fourth, that's one order, okay? This one is equal to this, right? This is denominator. And then the fourth step is to solve the new estimate. Level steps of the derivation steps in the Gauss method, okay? So SV plus 1 is equal to the initial gas plus the delta x in that step. Okay? Any problems?
I think that we will solve this problem when we
Okay, so I give you some one example, okay? Okay, so just like to solve these functions. Yeah, x squared plus 2 equal to 0, right? X squared equal to 2, right? Right. We know that quite easy, the answer will be the negative inequality square root of 2, right? Or if you are doing the Newton Raphson examples, this is delta, right? This is directions of the delta x, right? And for this, the square root of the x differentiation of the x equal to this, right? If the x square root of the x is 2 multiplied by x, like 2x, right? 2x. And for this here is the function is the xv square to the minus 2. Okay, so for this step, and for to update the delta x, we'll get this. The x minus this delta x.
Again.
Yeah. Okay, so no problems. So the actually here is the equations. So if we guess the x is 0, the answer of this function is 1. Okay, so the first step 1. So the fx will be the 1 square is still 1. 1 plus 1 minus 2 is negative 1, right? The delta x 1, right? 1 is 0.5. This 1 plus the minus 2 is negative 1, negative 1, negative plus. So that here is 0.5, okay? And then you get this delta x 0.5. Then we'll just have a second steps because we know that the update of the x is the x plus the delta x, right? X plus the delta x is 1.5. Okay, we see the x2 is 1.5, and then we get the delta x. And second step, we'll get this, and in the first step, we could see that 1.414 is approximate of the square root of the 2, right? So then here is how the Newton graphing is used to solve the functions. So any problems, questions here? We got simple examples, right?
I think we can try after we can find the problem.
Okay. Okay, so here is the spatial linear approximation. So here is the curve of this x square is equal to 2, right? So that the solutions to the fx equal to 0 is the point that this curve intersect with the x-axis, right? So this 2 point, right? 2 point. Alright, so Newton graphing. So that the Newton graphing methods, okay? So you see that for each step, because at the first step, we were gas is equal to 1 or 2, right? Here's the 1, here is the tangent line with the curve, right? Tangent line curve. And for each step, the first step, you can see that here is our gas, and then we get the delta x, here is the delta x, to make sure that how far from this curve, this point, this curve to the x-axis. We all know that in the intersect point, so this delta is equal to 0, there is no difference, no distance first x, the first delta x, and from this delta x we get the second guess, the second tangent line. Proceed with a quite small distance from the curve to the x-axis, and for third, the be a very quite small zero, almost the zero, so that we can see that the third step of this answer is the approximation of this intersection point. Okay, so you can see that it's very quite clear by this figure. You see the theory or the theory of these two transversal vectors. Okay, so we like this. We find the different tangent line of the curve, and we are solving the problem to make sure that the distance is getting smaller and smaller. Okay. So we close to the solution, the arrow decrease, okay? So arrow here, right, the distance. By each iteration, the distance will get smaller and smaller, right? The decrease, actually, and so we know the quadratic convergence. So then fx3 is knowing at this match, which would like to drive these functions to zero, because our target is to solve this function when this function is equal to zero, right? So that it is this match. So the stopping criteria here is when the fx3 is smaller than the c, then this criteria, okay? It's like this distance is smaller enough, then your stopping criteria. Okay. So also the result is also dependent upon the initial guess. Okay. Solution. Okay, and next we will see that if we have more than one variable in this function, how to solve this. We can how to solve this function's equations by using Gaussian methods. So the general case that x is an n dimension vector, the vector to say the x where we have 90 input, so that the fx, the function, will also have some mathematical function value corresponding with the input batch. And our target is then to solve the fx is equal to 0. Okay? Okay, so the Taylor series expression is written for each x match. For the f1 is here, right? The first function value, which is corresponding to the first input value. At 1, the first, right? The first atom. The first order atom, the second order atom. You can see we are going to wrap up the following items, so that we will get to use this, and we will get to start the higher order atom terms. Okay. So this is the f1, the first function value to the x1, and we will repeat this to the xn, right? The stand shape, right? Stand shape, In that case, we're going to write about you can say that the fx and plus the first order, second order, third order, and we will discard all the items from the second order. Okay, so here is only the first order, right? The fx plus the first order. First order is the first order differentiation of the x and multiplied with the delta x. Just like this. Right? Here is the fx value. Here is the delta x is the arrow item. Here is the slash item. Here is the matrix. Okay, so you can see that for the first one, because we only calculate the first order differential, right? So the f1 x, but in each fx, it will have the difference x1 to xn, right? Has the n variables. So the first f1 by x1, f1 by x2, according to the f1 differentiation by the xn, right? And then x2, f2 to x1 to xn, so the fn, x1 to xn, right? So here is the matrix, right? And we're putting a name for the Jacobi matrix. So and by the matrix of the partial, there will be active, knowing, and Jacobi matrix for this. Okay. And so don't worry, if we have maybe 2 or 3 variables, we only have 4, 1, 2, 3, 4, or 1, 2, 3, 4, 5, 6, 7, 8, 9, or 9 item matrix. Okay? Okay, so that by the same way, there's the derivation of the Newton-Raphson methods to the scalar case, right? We will approximate and we will push through the high order items, high order terms to only to the fx plus the first order terms. Okay. Okay, and the solution or the package of our Newton-Raphson methods is to get the correct answer when the fx is equal to 0. Right? The same with the scalar case. The scalar case, the fx is equal to 0, and here is only a matrix. There will be maybe multiple variables in each function, but also this is equal to 0. Okay. So that we'll put the fx to the fx plus the jx factor the delta x, like this. And then here is our package or corrective equations. Okay. So we'll put some transformation. We'll get this delta x to the next set. Then the delta x can be described by the Jacobi matrix and the fx. And so by the same way, so the update of the x is equal to the x previous x plus the delta x. And for because the delta x is equal to this, we're going to put this expressions here. Okay, so xv plus 1 is equal to the xv minus the jxv, the Jacobi of the xv. So as the denominator, and the denominator is the fxv. If I read on here stopping criteria, fxv is smaller than this. Okay. We'll see one example. Okay, so it's quite easy, right? It should be only two variables in this x. And to find the function, the f1 is equal to this two plus multiplied with the square of x1 and plus the square of the dot x2 minus h. The second function is the square of the x1 minus square of the x2 plus the multiplication product of the x1 and x2 and minus 4. Okay, two functions in fx, two input in one x. Okay, so symbolically determine the Jacobi method. So everybody will know that how to calculate the differentiation of the two. Okay, you know that. Just like for this one, for f1, and we will get the differential according to the x1. Okay, so in that case, f2 is equal to the constant value.
It's 0.
Yeah, it's 0.
And the 8 is also 0.
0, 0, so it should be 4x1. But for this, when we get the differentiation,
It's
according to
1.
x2,
Then that is 1.
so x1 is 0, right? 0, so there will be a 2 multiplied with x2, right?
Yes.
So you know that
Yes.
maybe in the examination you need to use your calculator, or for the essay case it will be quite easier. Cases you can just use your hand handwriting to calculate the Jacobi, right? Because there will be, we have no mathematics, no laptop during the examination, so you need to use your calculator to get this. The Jacobi matrix is the key step to solve the Newton Raphson method. Okay. Okay, so we'll get this one. So that as long as we have gotten the Jacobi matrix, so here is the equation that x1 equal to negative Jacobi matrix as the denominator and the fx as the denominator. Right? So that copy them. Okay, so we will guess the initial value is 1, 1, right? And for the x1, we could use this feature x minus the inverse matrix. And also, if you have calculators, you use your calculators to get this inverse of the matrix. Okay? If you do not have, so I remember that I told you that one method we'll see is A, B, C, D, right? Because this matrix,
Transfer this one.
yeah, the inverse matrix is equal to the unit matrix. Look for that unit matrix 1, 1, 0, 0. Unit matrix is that only the diagonal elements in the matrix is 1, 0. So that you have the four equations and 4 variables. You can calculate the A, B, C, D by each. But if you feel it, maybe it will be difficult or waste your time, to remember to bring your calculators. Okay. Okay. So here is the first step. And multiplication of the matrix, everybody knows, right? The first row, the first column, and the first row and the first column, right? Here is the first row column, here is the first row and the first column, right? So that for the Jacobi matrix or the Reactive method, the relation of the matrix is required, okay? At least you need to know how to use the calculators. Okay? So we get the first to reach value. This is the first step. And then this value will be used as the input, right? Or in the second step. Estimate work like this. And at each iteration, so we'll check that the start criteria, right? So the FXB, whether it is less than the stopping criteria. Okay, so that when the fx is more than the stop criteria, so the iteration will be stopped and you get the final score. You will get the final solutions. Okay. Okay. Do you need a break?
Break.
Break.
Break. We can take a break.
Okay. So we're okay. We'll start at the 10. Okay. Oh, next is also about the Newton-Raphson. So.
Yes, এক না সবচেয়ে ভালো এক যে যেখানে ছিল বাক্কাল রেডি
জিরো থেকে
জিরোটা ধরছো এটা জিরো হলো প্রথম মান কিন্তু জিরোটা গেস না গেস হলো কি ভি
প্রথম অঙ্কে
এইটাতে যদি তুই এক দিয়ে ভাগ যাস তাহলে এটা
আচ্ছা এই অঙ্কে এইগুলো আমি এটা আসলে পুরি কোয়েকশন থেকে
এই বিষয় সুদীপ ভাই অ্যাপ্লাই হলে মাইরো মারছে কিন্তু এই
কি মানুষ নাই যে হালা কইতে এই কাজ করে দেয় ভালো মঙ্গল
এটা আমার
কলি দোকান শুধু ভালো এই দোয়া করে এটা কবে আমরা ব্লাস্ট এ এটা নিয়ে যায় তো এই যে হার হোগা দেবে আচ্ছা না দিলে না এই যে এখন ময়লা কত বড় আমার হাত দিলে তো হ্যাঁ
আর এই মাসে
V2 পাওয়ার V এটা কি মানে কি এই ইকুয়েশন থেকে না এই যে সুতরাং ধরে V2 পাওয়ার V কি আমাদের বের করতে হবে এখানে
এই যে মানে V2 পাওয়ার V না এই হলো V প্রথমে V মান যখন 0 দেয়
হ্যাঁ
0 দিলে V পাওয়ার কত V2 পাওয়ার কত 1 তো 0 লিখলে আমি দেখতেছি 1 লিখলে এইটা
কিভাবে
এটা আছে কি তোমার 1 5 minus 14.79 minus 1 plus 0.5 B2 না B2 পাওয়ার যেটা কি B এখন B2 পাওয়ার B2 লই যায়
মানে এই ইকুয়েশন আপডেট ইকুয়েশন যে বের করতে হবে
হ্যাঁ
এই ইকুয়েশন থেকে এইগুলো বের করতে হবে
এটা এক একটা করে এনে দিতে হবে V2 মান আছে মানে এটা 1 0 এর পাওয়ার হলো 0 হ্যাঁ এর মান 0 মানে 1 সেম ইকুয়েশন আছে আর 0 হলো কাল দিবেন এই লাইনে দেবে ঠিক আছে
ওয়েট
minus e 5 plus 15 into 1
to get
এটা তো 0 এটা তো অ্যাঙ্গেলটা সেম হয় না না এটা তো 0 নেগেটিভ কোনো মান আছে
কি আচ্ছা 0 হলে এইটা আসবে আমাদের মান ওকে এই কোশ্চেন থেকে যখন g এর মান 1 হবে তখন এটা আসবে
এটা আমি বাইরে করতে পারি
ঠিক আছে এইখানে কি আচ্ছা v1 1 হয় তো তুই ক্যালকুলেশন করলে হয়ে যাবে
হ্যাঁ এই ওটা ধরে 1
আচ্ছা এদিকে আচ্ছা v2 ইকুয়াল টু পাওয়ার 1 কত হয় এখানে ইকুয়াল কত হয়
এটা হলো মানে গ্যাসের মধ্যে একসাথে মানে তোর যদি পাওয়ার যদি এখানে বুঝছো পাওয়ার 2 দিলে কিন্তু তোর অ্যাঙ্গেল চেঞ্জ হইতেছে না যেমন তোর আমি দেখাই যেমন
আসলে আপনি ধরতে কত থেকে 0 থেকে আমি যদি 1 থেকে ধরি
সমস্যা নেই
হ্যাঁ যে কোনো ম্যাথ এভাবে ধরতে পারবি
এটা তুই যেই ধরবি না তোর অনুযায়ী তোর একটা সিরিয়াল এগো
কত পর্যন্ত যাবো কাছাকাছি
4-5 আগে আমরা বিআইপিতে ধরো তাহলে 5-15 ধরো 5টা ভ্যালু বের করবি
মানে ওই আপডেট থেকে বের করতে হবে
এটা স্কয়ার রুট যাচ্ছে এটা স্কয়ার দিলে অনই হবে বল ভাই কি হোমওয়ার্কে মানে অ্যান্সার লিখে দিয়েছি
নেক্সট দেখো এই মুখ হচ্ছে না এত টাচ করতে গেছ না
না বেটা চোখের গুলো পরে কত দিন
কত
আমার যায় আমার
স্যার ইলেকট্রিক টার্গেটটা গেজ দিতো ঠিক আছে মানে
এটা তো ইচ্ছা রে ভাই
এটা কোন ইকুয়েশন থাকবে
শুধু তাই এটা হলো p2 দেওয়া আছে এটা লাগে তো i2 ধরতে হবে তো এটা লাগে আর ইকুয়েশন 0 মানে ডাবল ইকুয়েশন হবে ঠিক আছে আর h2 এই তো সেই ইকুয়েশন এটা pi minus pjq and s of the equation
ये করে এটা করে একটু বের করতে
y21 y22 y21 y23 y
এটা যদি না এটা করে তো
to 1 so 1 over 2 plus 1 over 2
এটা বের করা
কই বের করছিস
জেড টি গেলে কিভাবে বের করতে বুঝছ না এখান থেকে
আরে বোকা এই যে ডাইরেক্ট ডিভাইড করে দিয়েছি দেখছিস এর মধ্যে তোর আসবো ইনস্ট্যান্টানিয়াস ভ্যালুটা বুঝছ না ডিভাইড করে দিয়েছিস কি এটা রিয়েল ভ্যালু বাইর করে দিয়েছিস
এটা দুটো প্রজেক্ট আমাকে লাস্টে দুটো আমার প্রবলেম ছিল
দেখ ইনস্ট্যান্টানিয়াস
আপনি বলতে না পারলে সমস্যা নাই
সমস্যা নেই তাই না
ট্রাই করো আর সেটা বলছিল যদি না পারো দিও না
দিও না
হ্যাঁ এত কাহিনী করে তো লাভ নেই আমি দিতে যাচ্ছিলাম না তাও করছি
নাই দিয়ে দেবো
এখন কথা হয়েছে যে কালকে যে একটা ট্রিট দিলি এত আমার সেই ছুটাইছে ভাই তোমার খালি বন্ধু আছে এরকম বন্ধু সমান নাই
আমি সিএবলে দিছি আর আমি ভাবছি কালকে ডাকছি স্যার
ওকে এই জানো
আর তোমার সামনে তো জ্যাকরে কোয়া যায় না অন্য এটা তো
এ বলতেছে ঠিক আছে হ্যাঁ
তোরে কয়বার ডাকছি যাওয়ার সময়
এসে শিয়া বলতেছে আমাদের এরকম বন্ধু নাই
শিয়াবে আমি দিছি না শিয়া আমার এই কথা হয়ে গেল
ভাই কি ট্রিট দেয়
শিয়াবে আমি দিছি না একদিন
আবার একটা কথা খুব খারাপ লাগছে যে ট্রিট দিলে ভালো আমরা স্বামীকে ট্রিট দেই না
এই জন্য
খুব খারাপ লাগছে এটা
কে কইছি
কয় কি
বুঝছেন আরে বল বোকা শিয়াবে আমি অলরেডি দিছি আর অলরেডি আমি একদিন খাবার কিনে দিই তাই শুনো না
ওই যে ট্রিট দেয় এর সাথে স্বামী যায় না আমি যাইতে চাইছি তুই আমার টাইম নিয়ে রাখ
ওরা মেহাজনে তো হয়তো জ্যাকের এই করছিল কিন্তু ওই সময়টা করা না যে খাইতে দেয় কারণ মনে তো অনেক কোনো বানিয়ে
আমার এই যে সে আবার এই ফিমেল নিয়ে যায় কত খাইতে বলে আমি তো খাই
আরে বোকা তো তোদের তো বলা কথা তুই যদি না বলো তাহলে তুমি বলো
আমি কত
তুমি আর
বলবো
দেখে আর আমি নাম ধরে ই কর আর পোলাটা সাথে করো
তুই আমাকে কত কি বলবো
এখন ও তো তোরে কমই কয় আমি তো দেখি সত্যি কমই কয় তুই তারা নাই করে লাস লট করে
তুই ওটা এর জায়গাটা পছন্দ করতে কিন্তু জানি না
আমার দেখে বন্ধু আদিকালের বন্ধু দেখ
আপনি কেমন বন্ধু
ঠিক করে না
হ্যাঁ
আমি দেখি দেখি তেরো তো ওই লাগে কি লাগে মুদি না দেখি দেখি
আমি লেখা না
দেখি দেখি
কিন্তু টিকে
আরে ঠিক আছে
সাকিব ম্যাম একটা কল কেন রিড দোস্ত আজকে একটু কাজ সময় পেয়েছে লাস্ট পেয়েছে নাকি
তাই এই যে ওর লাগে একদিন আমি এনে খাবার নেই কিন্তু আইডিয়া নেই ভাবছি ওরা সারপ্রাইজ দিলাম কিন্তু দেয় নাই তারপরে তো সে তো একদিন ক্যান্টিনে নিয়ে খাওয়াইছি আমার তো দাঁড়া দাঁড়া আমার একলা সবাই না দিতে ফাঁকে যাতে দিছি এখন আরো তার নেক্সট আর একদিন দিয়ে দিবি কারণ আর ছিল না
এই কি ক্যাবিয়ার মুদি
কে কি
তা তুমি এর গার্মেন্টে আমার সাবাস চলাইছো কি
আরে কালকে ওটা
আমি
আমি
তো অতি সোদা নাই তোমার এখন একটা জিজ্ঞেস তোমার সোদা নাই তুমি গার্মেন্টে কাউকে
আমি বাট আমি যে ওই যে কালকে কন্টিনিউ বসে আছি আমি না দিকে আমি বলছি আমি তো সত্য কথা বলেছি আমি এর মতো ঘোরাই খেলে চাই
কি করে তোমার সোদা নাই জানে
বললো আমাদের এরকম বন্ধু নাই আমরা স্বামীকে খাওয়াইতে পারি না
বন্ধু কি আছে
কেউ কয় আগে না নাকি
সে আসবে না
বিকেলে আসবে আস্তে আস্তে অনেক টাইমেরও নেই ফ্রেশ হতে পারবো না মানুষের জীবনটা দেবো না এসি মেশিন ব্যবহার করছো জমা দিত
না হয়নি ওইগুলো তো জমা
ওদের ওটা প্রবলেম না কিন্তু কি দিয়ে
আমার তো
আমি তো করিনি এখন এটা কি করতে হবে এটা প্রবলেমটা কি না
স্লিপ নিয়ে স্লিপ এটা শারীরিক প্রবলেম আমি
দশ কি বলতো এগুলো
এগুলো
করতে হচ্ছে
যে একটু এসিনে এলে ইলেকট্রিক মেশিনের যে কোনো ইম্পর্টেন্ট একটা সাবজেক্ট ভাই আমার একটা কথা সেই মনে হলো কি হচ্ছে ভালো আমি করলাম আমি অবাক এটা আমি বসে গেলে মনে হয় আপনি কালকে কিন্তু একটা মায়ের কি পাস কারণ তুই ওদের পানি দিচ্ছিস
এটা ওটা দেখো প্রমাণ আছে
প্রমাণ তো হয়
দিছি কিনা এটা কোনো প্রমাণ আছে
আমি কেন দেবো
আছে ভাই
আমি কেন দেবো
এটা সব দেখি
দেখ তোর পিঠে লাল লাগে দিচ্ছে দেখ
এটা আছে না এটা আছে এগুলো ওই দিন মা আমার হয়ে গেছে তো বা
আমি যাওয়ার তো দাঁড় দিচ্ছি
আজকে আজকে দিল
মার 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 দে দে
না না আরে কি হলো একটা দিল তো দেখাবো
সুইড আপনাকে একটা মাইকে খারাপ হলো
এখন Sila na, meron daw sa
Kami.
Man check. Sana kumai. Slip.
睡觉。
是的。 Correct me out of it.
Current I, right? That current is equal to the sum of the molecular charge of the admittance and the voltage. And for doing so, we're get expression of the complex power and the admittance. It can be derived by doing this. And for the voltage, is the voltage with the angle. And for the difference of the angle for the voltage I and the voltage K, right? So it is the I's angle minus the K's angle. So the Alice formula, you remember?
Yes, sir.
Right? Is equal to the cosine theta plus the sine theta j. Right? Okay, so in this case, P and Q, right? We know that P and Q can write down by doing so. Can write like this. Because we see that the V actually is equal to the V, the magnitude of V equal this natural exponent, right? Exponent is J theta, right? So that for this V is equal to this VI and VT, right? J. And this is not where here is the admittance, right? We write down the admittance in like this. And then we'll get another expression of the complex power, okay? So the magnitudes of the voltage I, voltage K, so theta, the difference of the theta plus the J sine theta, and difference of the angle, and here is expression of, and this is the admittance of this mutual admittance, right? G and P, right? So that we're resolving into the real and the imaginary part, the P and Q, right? The PI and QI. Into the two stage, into the two parts, right? Here is the real part, here is the imaginary part. Okay, so I have problems for this. Okay. Okay, so we were using the Newton-Raphson method, iteration method, to solve the power flow in this lecture. Okay. So you can see in the Newton-Raphson power flow, we're going to use this method, iteration method, to determine the voltage magnitude and the angle in each bars of the power systems to satisfy the power balance, okay? So that we will need to solve the power balance equations for this two. This is the real power, this is the reactive power. So conductance, the cosine of the different angle, and that's the susceptance, I put the sine of this angle, right? Here, this indicates the imaginary part, it indicates the real part. Okay, so these two. So the power balance equations, so for convenience, we're just to write down, and from these two equations, we're just to write down here like this. We assume that this part is called real power functions of the box I, right, the Px, and here the reactive power functions for the box I, doing like this, so that the power balance equations can be written down, can be simplified by like this. Okay, so in next two power balance equations, we're knowing that we refer the P and Q is a function that drives the flow from box I into the system in terms of the voltage, magnitude, and angle. Right? The I means the box I, and it means the power flow that flow into the systems from the box I. Okay. And we also know that the G and D, G means the generation, semi-large, the power flow. D, divine, receiving the power flow. Okay, G, D, two different types of these two power flow. Okay, and for system, we do a connect bars, and the rest two bars. The power flow problem, you use the power balance equations, power balance equations, these two equations to solve for the unknown voltage, magnitudes, and angles, because we assume that in these power flow equations, we know the PQ, right? We're using the PQ boxes, so that the unknown parameters in each bars will be the voltage, magnitude, and angle, right? Voltage, magnitude, and angle. So that then we will use these to define the power injections at the snack bars. Okay. So that we start we'll start at the power flow variables, so that let's assume that the first bus and the second bus will be right? It's okay. We then need to determine the voltage angle and magnitude and the other buses, right? We'll solve with that. So we remember that the x is the input, right? And what we are unknowing that because the first bus is the select bus, the V1 and the theta 1 is knowing, right? And for this, from theta 2 to theta n, no V2 to Vn, the voltage magnitude, the voltage angle, and for the Fx is the power equation, power balance equation, right? We assume that this one is 0, so this is the power equation, power function. P2 to Pn, the 2 to 2n, right? The 2, right? So that for the Newton-Raphson power flow solutions, the power flow is solved using the same procedure, okay? By the same way, the summary of the Newton-Raphson method. So for V equal to 0, so we will assume an initial guess of the x as 0. As long as the fx, this power balance equation, is still not then the solve criteria, right? We're using this iteration equation to update the x value. The x value is the target value we need to calculate back the angle and the magnitude. Okay? So that the key point of this method of this interrupting methods of power flow calculation is the Jacobi matrix, right? And the Jacobi matrix. So Jacobi elements calculate and now it's by differentiating each function fx and with respect to each variables. So that here's an example, and now as the fx is for the box I, the real power equations. Here's the real power equations that knowing that the differences for the real power and the reactive power is the cosine plus the sine, but here is the sine minus the cosine. Conductance, susceptance, so make sure that you convert the two into the differentiation and change the plus to the minus, okay? For doing so, right here is the iteration x, right? So this one, if we get the differentiating with respect to the difference to the box I, so how to do it? So do you know how this do? Calculate this do. What is the differentiation of the cosine is equal to
minus sine.
minus sine, right? How about sine?
Cos
Sine, cosine. So do you remember that sine is cosine, but however cosine
Minus
is
sine.
minus sine. Do not forget this,
Yes,
okay? Yeah, differentiation. So this due is constant power constant 0. Okay, so and now as J is not I, right? J when I and J is not the same bars. Okay, we can write down like this. Okay, so in this step for I, right, sigma B is from 1 to n when the K is not equal to I, right? We'll write down like this. And because this is Fi, right, we need to get a differentiation function with respect to the box J. Okay, how to get this?
A5 by
So why the sum is disappeared here? Why is the sigma or why the sum cycles disappeared here?
Lucky. Please say this
Yeah.
question again.
No, you can say that in this section for I, right, here from P is equal to 1, this means that the K is in V1, V2, V3, and to Vn, right? And the sum of this order of these n variables, right?
So K equals it.
And for here, because only this is differential with respect to the variable J, right?
Yes, sir.
So as long as 1, 2, 3, 4 is all the constant value, right? So it has nothing to do with the J, right? So that is the only way that it's all variables in this sum functions. What we need to do is that only J can be disappeared here, right? because all other variables in j equal to 0, nothing to do with the j. Right?
The differentiation about z.
Yeah, differential with z, right?
So,
You could see when k is not equal to j, k is not equal to j, k is not equal to j, constant, 0, 0, 0, 0.
yes, sir.
Okay, so this one is 0, right? So as long as the k is not equal to j, so all of these two are 0, right? 0, 0. So that there's only when the k is equal to j, bi, vj,
Bj.
right?
Yes, sir.
gij. So in this case, if they are not equal to 0, right? And so say sine
Ij.
is equal to cosine, right?
Okay, it's minus.
cos theta minus sin theta.
Z sin theta minus cos theta.
উল্টাই আমাদের জানি
সামান নষ্ট না তোমার সামান নষ্ট না
So in that case, do you think that this one should be the negative or the positive?
is positive, sir.
Why?
Because we do it this differentiation I over I. So we get di dk and minus zik
Okay.
sin theta ik dik
Yeah.
cos theta ik. So that this I j k.
Yeah.
So we just transfer I to z, z to x. So this is angle is same.
That makes sense, right?
So this is changed.
Okay. So, is there any other problems about this one?
Because it changes from k to z.
Yeah.
So our angle is same.
Yeah.
So this sign is going to be positive and this cos is going to be negative.
Yes, you are correct.
This is, do you understand now?
Know that? Everybody know this?
Mean, do you understand?
Huh?
Mean, Shamin, do you understand now?
Why positive? So you can explain this to me once again?
So এই জায়গায় যেমন কে আছে না যেমন কে ইকুয়াল জেরো আছে আমার ইকুয়েশন এটা এখন কে এই জায়গায় যদি এই জায়গায় যায় যেমন এটা 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 হলো কি পাই এটা জিরো এটা 3π/2 এটা হলো π/2 ঠিক আছে এই জায়গায় গেলে যে অ্যাঙ্গেলের সেন্সটা না অ্যাঙ্গেলের সেন্সটা ফলে এটা হচ্ছে প্লাস আর কলের জিনিসটা মাইনাস।
Okay. Okay, so next we'll start to using one examples to box systems, right? Okay, so this Newton Roxing particle determine the voltage, magnitude, and angle of this box tube. Okay, so sensing that the box one, we also will assume that the box one is the snack bars, and so the base of the sequence tower is 100. Okay, so that here is 1 per unit, 1 per unit, and this is 1, 2, this is 1, right? Like this unknown vectors, x is equal to the theta 2 and the magnitude d2, right? y bars are easy, right?
Is
The serve admittance here, zero because here is the z, right? Z should be get a inverse
node
of
1
this
is,
one.
but node 1 to 1 is minus 10z and 1 to 2 is 10z and 2 to 1 is 10 and 2 to 2 is also minus 10.
Yeah, because z1, j, right? Because
Only
this,
only one impedance.
yeah. The denominator y, and if we were multiplied with j square of j is equal to the negative y minus y. So the y here is minus, but here is negative. So the line indicates here is actually the magnitude is negative 10j here.
This one.
Okay, so this power balance equations, these two, right? Okay, because we know that the node in the bus 2 is the node, right? Bus 2 real power is 2 per unit, and the reactive is 1, right? 100, 200. So that we can do use this power G and D here to write down here, right? Here is only 2 buses. B here is also the thing, right? 0, 0 minus the 10j or the 0 plus the 10j, right? The G, the conductance is all equal to 0, right? So this is so G is equal to 0. So there is only the acceptance D here, right? So that is the y v2 v1, right? v2 v1, right? And from the theta 2, why theta 2 here is because here we assume that it's a slack bar, so we will assume that here is 0 degree, right? 0 degree, so that the difference angle of this is only the theta 2, right? Theta 1 is 0. Theta 1 plus 1 is a slack bus, right? So that here the full is the negative 10 cosine, here is the positive 10 sine, right? And here the 2, because the real power generation is 1, right? So that here is the 2 plus 2, and here is the another 10 here, right? Plus the 1, this 2 is equal to the 1 unit per unit. Okay, so
B2 square minus B2 square into 10 passing B2. No, that's what this one.
okay. Here. B is here, right? Okay, because that
Exactly, this is the form of the line. So,
You could say that here, because here is the sum of this VI and VT, right? So that VI is V2 and VT is from the V1 and V2, right? So it's actually, so the V1, V2 is a V2, V2, as well V2, as this, okay? No, here is the sum, right? Here is the sum.
V1, V2, yeah. That's
Yeah,
why
V1.
it's here. V1 and V2.
V1, V2 is equal to this. V2, and for the V2, so that this G is I is also the Q is the third, is the third on top of
Also,
the
that
Q.
you can get this then, yeah?
Yeah. And for the third of this here, minus 10, right? So that is the 10. 10 minus 10 equal to positive 10.
And this one for this.
Yeah. This is the generation, the negative generation, and plus the demand, right? So the demand. Because here is the 1 per unit, so you can just do A, them together, okay? So the power and reactive power. Because of this here, for here is also, the Q is also the reactive power. So here is only one, right? The P here, there is no generation. So the 2 is also because there is no generations here. Okay. And for this function, you can say that V2 square V, right? 2, because here is 0, right? Because there is a low conductance. And then for here, 2 is 0, sine 0 is 0, but cosine 0 is 1, right? Yes.
Yes, sir.
So that's why here there is no square of the V2.
Okay.
Okay. Here. For this function,
For this is V2, V1, yeah? No.
V2 line is here, right?
Yeah.
V2. Okay, so for here, cosine, this theta, because this is the V2, right? So this theta is 0, this is 1, but however, this is 0, because there is no conductance, right? And but for this B is not 0, but however, sine is 0 is 0. Why here? Because here is cosine. Cosine is 1. This is not equal to 0. This is not to 0. So it's here.
Now if B equal B I equal sin theta 0, so how to get 10 sin theta 2?
Here, it's very difficult.
Yes, sir. How many 10 sin theta 2?
We want
If B equal to sin theta equal to 0.
0, but however, for here, right, I is not equal to k. Because I is a box 1, right? In box 1, we assume that it's negative bar, so we assume that there is a 0 degree. So that the theta q here is 2 is the angle of the box 2.
Theta 1 equal to 0.
Yes,
Not
because we assume, you can see that we assume that here is here you can see that it is 0, and here we assume that it is slack box. Slack box. And generally, we assume that here is 0, right? So that the angle here is 0, so that the difference of the 2 and 1 is the angle of this, here is 0. Okay? So 0, so here. this. Because our equations are this one is equal to 0, this one is equal to 0, right? So that we assume that we'll write down the what P2x and Q2x. Let's do like this, okay? The Pi is equal to the generation, the negative generation, and the sending out the demand power, okay? Write down like this. So this part is equal to this, right? So this is the difference of this power flow, and here is the sending out and sending in. So there is the power flow from the outside or from the other part of the system, okay? So we can write down like this. And this is here equal to 0. Okay? So that make sure we need to calculate the dichotomy from this to this. So do you know how to calculate this one? Find it that P2, theta 2, like for example, P2, theta 2, sine is equal to cosine, right? Okay, because P2 is 10. Because here is the 10, right? 10 plus here, right? And 2 is equal to 0, of 10. P2 to the P2.
So 10 sine 2.
Yeah.
So 10 sine 2.
This, right? Because the P2 is equal to 1. Because P2 is equal to 2. P2 is equal to cosine is equal to negative sine.
So times
negative, positive. Yeah, 10 V2 here. Because and V2 here is a constant 0, 0. For here, for V2,
minus 10 cos
and this
plus
is 1, and minus 10 cosine theta 2,
plus 20,
and 2, 1 third V2, 2 V2, and here 10, 20 V2.
yes sir.
Okay? So the copy function. Okay, for the first step, we're guess that the theta, the angle is 0 degree, the V2, the magnitude is 1 volt. Okay? So that calculate the first step. Doing so, use this angle here, back side 0 equal to 0, 0, 0, right? And for the cosine, 0 is equal to 1, 10 is the negative 10, right? Negative 10. And here is 2, because here is the 1, right? Here is 10, negative 10 and 10 is 0, so that here is 1. Okay? So we get the function value in the first step, and then here is our new input, sending in our equations, right? We can get the new Jacobi function, right? New Jacobi functions here equal to this and equal to this.
So mom can be the same as this.
Okay? For this Jacobi, we need to use this initial gas here, initial gas this. For example, so the theta is 0, 0, 0, theta 0, 1, 10, 10, 1, 1, okay? So you know Jacobi Jacobi, you know the fx, you know the function value, the inverse of the Jacobi calculator, or your hand is on your own. My story with this function value, and here is the initial guess. So that here in the half state x1 maybe refer to this.
It's so loud. No?
Okay, okay, this one is a power.
Which give me here.
Your neighbor.
I think
Yeah, last I
This back page.
back, yeah, this one.
This is the differentiation.
differentiation, right? Q2 differentiation with respect to V2, right? V2, so there V2 is this, so you do 90 cosine theta to here. V square, how to square 2, what is the differentiation? 2V1, right?
Oh,
2 and 10 is 20. Then
So loud.
okay, so we are getting a different code for you to calculate. So if this one is in the examination, can you just to solve this? Okay, use your calculator.
When we go home.
At home, examination, you need to finish all the formulas within the classroom. But you have the calculators, right? Okay, now sending these equations for you, the Jacobi equations for you, and only for these steps.
This is okay, sir.
Okay, right?
Sir.
So actually is okay because I will leave this for you, leave this for you. Okay, so all equations is for you. Okay, so these equations I think it's easy because we maybe only. So alternative is to keep the reactive power balance equation Stesdy, but to write a constraint to generator classes. Anyway, we can see an example. 3 buses. What we do not know, so the 2, the 3, the 2, right? Because here is 2 generators, here is the node, right? So the fx, P2, P3, and 2.
What we must be useful.
Okay. Because you can see that for the bus Q P2, P2 and the demines, right? P3 and demines, and Q2 and Q3, and because here is a node, so that we do not know the, because the PV bars, right, we do not know the reactive power, so that we will name the Q2 here, okay?
Sir, P2x plus PD2.
PD2, right?
Yes.
Here is the function value.
This is the equation.
Yes, equation.
Okay, sir.
The same P2 here, right? P2 and Q2 here is both the nodes, right? So we need to what we need to solve is the reactive power of the bus 2 and the voltage angle of the bus 2, right? Example, okay, so the PV buses, so we can write this. So exactly that's unknown variables we do calculate, and that's equations what we need to satisfy. Okay. So reactive power balance. So it's satisfied by choosing the reactive power production to match the requirement. Okay. Constraint to the Gauss iterations will be more complicated. we're completing the algorithm anyway, so we'll start to see. Okay, so PB bars is it seems that not required to know. Okay, so you need to just to know. Here is maybe the same method, same way to calculate PB buses. And the third, we're going to calculate the modeling, the voltage dependent nodes, right? To see that in the previous node, it has nothing to do with the generator, right? It is independent with the generator. But for this, we need to consider that the nodes were dependent with the voltage generator, okay? Constant power, because the power flow can be easily extended to include the voltage dependence with both real and reactive nodes. So we're just utilizing this PPI and PPI in the function of the voltage magnitude.
T square.
Okay. Because dependent nodes, right, the generation is the same, but for the power, real power and reactive power nodes of the dependent, we need to consider the voltage magnitude, okay, because it's related with the voltage magnitude. Okay, so in the previous two box examples, okay, so the examples we used to calculate. Here, right? We assume that here is the constant node. But here, with corresponding per unit of the 2 and 2 plus 10 1J, right? 1 for reactive, 2 for real power, right? So that the equation here is turned to this, because here the V2 square, V2 square, V2 square. So, okay, so the power Jacobian is a little bit different, right? But it is still the same way. For this is the theta 2, right? Theta 2. So it is nothing to do with the V2. What we need to focus on is just when the input or when the differentiation in respect to the V2, right? Here, it's like 2V2 is 4V2. And here there is an actual 2V2, right? So it's just a small change, very small change of the previous Jacobi matrix. So that again, so we're guess that V equal to 1, theta equal to 0. This is the Jacobi, right? To calculate the function value x0, we're going to get the function value. The Jacobi is maybe a little different. The previous Jacobi is 10, 10, 0, 0, but here is not. So that the x1 is equal to this. But however, here is the same, is actually the identical methods, okay? Except for only two extra terms here. So that in the same way, we can get also calculate this voltage dependent node. That more generally, so the nodes can be modeled as sum of the constant power, constant impedance, and constant current node terms. Okay, so that it's just a different cases of the different nodes in our real applications. And finally, if we need to solve the large power systems, okay, so most difficult or the key task is inverting the Jacobi matrix. Okay, so this is the most difficult part. So it's factorizing a full matrix is an order n triple square of the n operation. Do you know what is this? In cube. And it's actually we would say it's actually parameters or the criteria in the theory of the reliability. We call it the complexity. The complexity is that n means the number of the inputs. Okay, so that means how many time calculation or how many time iterations you need to using this algorithm to calculate, to finish your calculations, so that you can see that it is a very exponential difficulty when the n becomes very large, right? 10 equal to 10, 100 or 1,000 times of 1,000 iterations, so it becomes more difficult. So that amount of computation is decreased by recognizing that since y space that the bars of the admittance matrix is bars matrix, when there is very many zeros in the y matrix, so there will be Jacobi matrix, there will be also many zeros. And finally, using sparse matrix, computation order will be decreased in half time, less than half time of the previous complexity. Okay, so this is a very overt advantage, especially so if we have thousands of the buses. Okay. So that the advantage of the multi-indexing. So the fast convergence is known as initial gets close to the solution. The margin rating of convergence, right? Because in our examples we have known that maybe at most 3 or 4 steps of iterations to get the final answers. Okay? But the disadvantage is that each iteration is a bit more difficult than the Gauss-Seidel iteration, right? Because U fair is maybe a little bit more difficult to calculate in Jacobi, inverting the effects, right? For the Gauss, it's very much simple formation of the iteration methods, but in the multi-indexing it's more difficult, right? And much more difficult to code, okay? But however, actually the multi-indexing is one of the most commonly used algorithm to compute the power flow. 15 minutes. Should we start next lecture?
No, nothing. Finish.
Finish? Is too difficult?
Yeah, okay.
Yes. Next lecture, power flow.